In this video I'm going to explain a rule called Simpson's rule, which is used for approximating definite integrals, and we're already sort of familiar with this kind of technique. So let me talk about what Simpson's rule is. It's a numerical technique to approximate the area under the curve, and therefore it allows us to approximate definite integrals. So still sometimes we're going to be faced with integrals which we can't integrate, which are maybe too complex for us to sort of integrate algebraically. And so therefore this is a technique which allows us to come up with a numerical approximation to that. Now we're already familiar with the idea of using rectangles or using the trapezoidal rule to approximate area under the curve and therefore to approximate the definite integral. But this is a bit more accurate than that because this uses parabolas rather than straight lines to approximate sections of the curve. So what do we mean by that? Well, let's say we had a function like this, y equals f of x, and maybe we're wanting to find the area under the curve between x equals a and x equals b. So wanting to find that area under there, and therefore wanting to come up with an approximation for this definite integral there, the definite integral of f of x between a and b. Now f of x is a continuous function between there. So we've already come up previously with the idea of, well, what if we split this up into sections? So we divide it up, let's say that's the first value there, x0, this is x1, here's x2. So we're going to divide it up into strips. This one here can be the nth value of x, and this one then would be x n minus 1. And in between there could be, any number of strips. So we've divided up into all these strips. Now if we were using rectangles, we'd be saying let's approximate each of these things here with a rectangle, and we'd have to, truncate at the left or the right value. And we can see that our approximation there would be a little bit inaccurate because in each of those rectangles we're either overestimating or underestimating the area. And so then we've said, well, let's go a bit more accurate and let's use trapezoids. So we're actually drawing straight lines between the tops of the points. And you can see already that's improved our accuracy quite significantly, but still we're approximating a curve with a straight line at the top of each of those trapezium. So what we're going to do now is, in Simpson's rule, we're actually going to use parabolas to approximate these. And so for every set of 3 points that we have here, we're going to use basically fit a parabola between those 3 points. So all sets of 3 points, wherever we've got 3 of those points, we're going to fit a parabola to that. And then find the area under the parabola and add all of those together. Now we do not need to be able to develop this rule. Simpson's rule is given to us on the formula sheet, and in fact it says all we have to be able to do is to use Simpson's rule with technology. So here's what Simpson's rule says. Maybe I should just move this down a little bit. And so we're going to say for an even number of strips n, so divided this up into an even number of strips because we need to take 2 strips at a time to get the 3 points. So 2 more strips at a time, 3 points, 2 more strips at a time, 3 points, and so on. So we need an even number of strips. And our rule says that it's going to be w over 3, where w is the width of any of these strips. We're going to evaluate the function at x0, and then plus 4 times the values of the functions at all the odd numbered values of x. So when we talk about these values here, we're going to talk about our 2 end values, which are x0 and xn. We're going to talk about our odd numbered values of x, so x1, x3, xn minus 1, and so on, and then our even numbered values of x, which are x2. Sometimes we call these values of y, the corresponding values of y, the lengths of these lines. Sometimes we call them the ordinates. So we've got our even, or rather our odd numbered ordinates, which are going to be the values of the function at x1, the value of the function at x3. Let's do one more, and then we'll just say plus dot dot dot. So we're going to add all of those together and multiply them by 4. Then we are going to say 2 times the values of the function at the even numbered x points. So these are the even numbered ordinates, x2, x4, x6 if we had one, dot dot dot, then plus the ordinate value at the very other end. So the other end, which is f of x sub n, and that's where, let's just define w is equal to b take a over n. So in other words, that's just saying we're dividing up the interval from b to a into n strips. So that's giving us the width of a single strip. Now, as I say, that formula is on your formula sheet, so there's no need to learn it. There it is there, almost a little bit hard to read when it's that small. But sometimes to remember this, if we were trying to remember it, we could say that this definite integral here is approximately equal to w over 3, and then we'd say the n's, so that's the two n ordinates. Let me write that a little bit more neatly. So the n's plus 4 times the odds plus 2 times the evens. So that's a way that we could possibly remember that. Now let's consider then a question, and we'll actually sort of do this using technology, because that's how we're told that we will need to be able to do it. So just pick a fairly simple one here that we could quite easily do exactly, and we could quite easily do even algebraically. So the second question in exercise 12F asks us to find the value of this one, to estimate the value of that integral using Simpson's rule. It doesn't even tell us how many strips to use. So let's do that, and let's do it using 6 subintervals, or 6 strips. In other words, n is equal to 6. So just thinking about that, we would have w is equal to, well, we're splitting the interval from 1 to 0 into 6. So it's going to be 1/6. And so therefore, our values of x, well, the first one is going to be at 0. x1 is going to be 1/6. x2 is going to be 2/6, and so on, down to x6, which is going to be 6/6, or equal to 1. So each of our strips there is going to have a width of 1. Well, let's go over to our technology and see the quickest way that we could work with this here then. So depending on the sort of complexity of our function, one of the things that's going to be useful is to define our function. So I'm going to say, let's let cos of x be the function, and we should be able to do this using a store. So let's say that's f of x. Alright, so the good thing about doing that is now I should be able to type, f of 0, and it should give me the value of that. Okay, so for my value of Simpson's rule, if I actually just go back to this one here, I'm going to be saying the integral from 0 to 1 of cos x dx is approximately equal to, so there's w over 3, and then I'm going to have f of 0 plus 4 times f of 1/6 plus f of 3/6 plus f of 5/6 plus 2 times f of 2/6. Now I know I could simplify that, but probably just helps here to make it clear that, or in this case makes it a bit simpler to see that those are the second and the fourth ordinates, the even numbered ones, and then plus f of 1. So that's what I'm going to be entering on my calculator screen now. So I want 1/6 divided by 3. Well, I guess I could enter that as 1/18. And then I want f of 0 plus 4 times f of 1/6 plus f of 3/6 plus f of 5/6, so they're the odd numbered ordinates, plus 2 times f of 2/6 plus f of 4/6, and then plus the final ordinate value there, which is 1. So I've entered all of those, and it's giving me an approximate value of 0.841. So let's put that down there. 0.841. Now I could of course compare that to the exact value, couldn't I, and see how it goes. So if I went, let's try that now, let's do the definite integral from 0 to 1 of cos of x with respect to x, and there it is there. So certainly to 5 decimal places or so, it's actually there's no kind of error margin there, so pretty accurate.